My name is Brent Corkum. I'm going to be delivering the first half of this webinar. This webinar is titled RocSlope2 Revolutionizing Rock Slope Stability Analysis. Next slide. Okay, as mentioned, I'm Brent Corkum. I'm the Chief Technology Officer for Rocscience. I'm also the Chief Architect of many of the Rocscience products. I'll be joined today by Julien Chaperon, the project manager for RocSlope2. He's also the lead software developer on the project as well. Next. Okay, a little bit about Rocscience. We're a world leader in developing innovative 2D and 3D software for civil, mining, and geotechnical engineers. We're dedicated to delivering industry-leading software programs, exceptional customer service, and unparalleled technical expertise that engineers can rely on. The company itself was founded in about 1996. We've had about 25 years. We started off 25 years ago with 4 people, of which I was one of those people. And we've grown now to a team of 80 people in 4 offices around the world. 10,000 users are currently in the process of using our software. Next. Okay, a little bit about our software suite. We develop products for geotechnical engineering and mining engineering, civil engineering. We have products in slope stability, slide 2 and slide 3. We have finite element products for doing slope stability, consolidation analysis, thermal, dynamic, tunneling, all these types of applications. Those are RS2 and RS3. We have borehole logging software, which is fairly new. We do settlement software, Settle 3. We do pile analysis software, RS Pile. We have 2 products that do rockfall analysis, Rockfall2 and Rockfall3. And we have a number of structurally controlled failure products, products that deal with joints and discontinuities, of which we'll be talking about one of those today, RocSlope2. But we've also recently released products called RockTunnel3 and RockSlope3, which do structurally controlled failure. And of course, we have Unwedge, which does underground structurally controlled failure. And I'll be talking a little bit about dips today as well. Next slide. Okay, the software ecosystem. We put a lot of effort into the integration of our products, integration between products. And I'm going to be dealing a lot today with that sort of right area, which has dips in it, and how dips is connected to RocSlope2 and Unwedge, RockTunnel3, and RockSlope3, which are structurally controlled failure modules. I also have a lot of experience on the left side with slope stability and slide 3. I won't be talking about them today, but it is really a major part of our software that they are integrated together, which makes life a lot easier for you, our customers. Next slide. Okay, so the agenda of the webinar today is I'm going to first talk a little bit about the evolution of rock slope stability at Rocscience. It goes back to the 1980s. Then I'll talk a bit about RocSlope2 approach to rock slope stability, brand new product. And then I'm going to talk about its practical applications. And then Julien will take over and talk about the key features of the product. And then we're going to give you a really cool demo of what it can actually do. Next slide. Okay, so the evolution of rock slope stability at Rocscience. It does go back to the late 1980s with Everett Hook and John Curran at the University of Toronto. I was a graduate student back there.
And in 1991, we developed and released, I should say, the very first version of S-Wedge. And it was done by a graduate student, Deep Shaw, a PhD student, who basically took the method in the back of Hook and Bray's RocSlope engineering text and implemented it. It was a vector-based algorithm. It worked fairly well, but there were a number of problems with it. Then in 2001, we developed RocPlane. That was to basically add to the types of modes of failure in rock slopes to analyze. And then in 2013, we developed RocTopple, both for block toppling, Goodman's method, and block flexural toppling. And in between that period, around the mid-2000s, we actually converted S-Wedge to use block theory, Goodman and Shee's block theory, to get away from some of these issues we had with the vector approach in the back of Hook and Bray. And we also converted our unwedge program at that particular time to use block theory as well. And then around 2019, we put a concerted effort into upgrading all of our rock engineering modules, S-Wedge, RocPlane, and RocTopple, and to add all the things that people wanted us to add. In particular, we added things like ponded water for when you shut down particular pit, and things like sensitivity analysis for bolt force. So we improved our bolt force algorithms, and we, through our M+ program, we had consistent updates through this particular period. And then around last year, we released a product called RocSlope2. And RocSlope2 it's extremely cool program. We had a webinar on it last year. It basically is takes the ability or has the ability to take joint and discontinuity location data and form not only wedges but multi-sided polyhedra in order to do stability and complex stability analysis of blocks. And you can sequentially remove them. You can use real pit geometries or slope geometries, and it's an extremely cool piece of software. And then in this year, we've released RocSlope2, which is basically a reimagining of S-Wedge, RocPlane, and RocTopple. To me, I look at it as, if I could roll back the clock to 1991, this is the product that I would make. And I'll get into a little bit of the reason for that. But let's move on. Next slide. Okay, let's talk a little bit about dips, because the workflow that we imagine for RocSlope2 is where you first have a series of joint measurements. They're usually in dips. They could be in another package, but you have a list of joints, and you first do a kinematic analysis with dips, which, if you're dealing with stability of rock slopes, obviously structural discontinuities are a major influencing factor for how the slope fails. If you're a ground control engineer or a geotechnical engineer or a civil engineer, obviously you have to look at the characteristics of these discontinuities, determine whether any of them can form blocks or planar failure or toppling type mechanisms that could cause failure of the slope, and obviously, you don't want any of these failures to impact local infrastructure as well. Next slide. Okay. So we talked about dips, where we're coming from with kinematic analysis. And the kinematic analysis, let me just say, is principally where you're taking just the orientations of the joints and figuring out whether, in the case of, say, wedge failure, you're daylighting on the slope face, and whether the angle of the intersection between the two planes dips at an angle greater than the input friction angle, in which case you can get failure of a particular wedge. It's a very simplistic algorithm. It's not limit equilibrium. It has very little physics associated with it, but it gives you a really good idea of whether you're going to get or expect failure on your slope. RocSlope2 is the next step in this process after the kinematic analysis. If you find that kinematic that you are getting failure, then you can go to a program like RocSlope2, which has the proper limit equilibrium physics. It creates blocks. It actually looks at the failure direction of these blocks. You can add loads, seismic loads. You can have water pressures. You can have complicated shear strength models, all these sort of things in it. So it's the next step in the process of looking at the stability of your slope. Next slide. Okay, so this is really the vision of RocSlope, as I was mentioning before, is that, with the packages S-Wedge, RockPlane, and RockTopple, which we had developed over that period of time, yet you basically had to use them all three independently, and you had to put in your geometry independently. You had to look at each mode of failure independently, when really you should be looking at the mode of failure at three types of failure: the wedge failure, planar failure, toppling failure. You should be looking at it all at once, determining, which is the critical mode, looking at all the factors of safety of these, not having to treat them all independently. And using these three programs, it's very, very error-prone, because you're basically creating the models independently. In RocSlope2, it's one model. It deals directly with dips, and it brings in that data, and you'll get a sample of that later on. Next slide. Okay, so what's the key differences between kinematic analysis and limit equilibrium? I spoke a little bit about it. Basically, kinematic analysis just considers joint orientation and an idea of friction angle. It can't do these complicated joint models such as Barton-Bantas power curve, or even more Coulomb with cohesion. It gives you an idea of what failure mode is possible, but it doesn't tell you what the critical mode of failure is. And of course, it can't handle support. It can't handle external forces. It can't handle pore pressures. And all these are extremely important mechanisms in the stability of the slope. While RocSlope2 obviously will provide much more realistic analysis. It'll create blocks for you. You can see the blocks. You'll see that in the future here. You'll be able to calculate factors of safety, probabilities of failure, all the things that you're used to doing. And you'll be able to look at external forces, pattern bolts, all things that we've added to this program. Next slide. Okay, so the default, if you're used to using a program like S-Wedge or RockPlane, you have a deterministic model, you put in a couple joints or one joint, and it gives you a sort of a factor of safety. RocSlope's built a little bit differently. It's really built as an extension of what DIPS does, and the fact that it starts with a combination analysis, which is basically you put in a list of all the joints you have on your slope. And what it will do is it'll go through all of those joint combinations, and it will tell you what your critical joint combinations are. And it will, give you all the different modes of failure. What are the critical modes of failure? You can add things like, basal failure planes to your analysis, and you can add sets and all the things that you're used to doing. But the big thing is that you can just read in that DIPS file, do exactly the same analysis right away, and you get an indication of the probability of failure. What is the critical mode? And one set of geometry for the slope. It's doing all of it at once. It's not 3 independent programs in one. It's the whole thing together as one working unit. Okay, next slide. Okay, so what are the practical applications for RocSlope2? Well, it can be used for bench design, for looking at probabilities of maintaining certain bench widths and back break distances and all that sort of thing. You can use it for, obviously, road cut stability, railway cut stability. You can use it for the design of open pits and support design in general, looking at things like pattern bolting, which does not exist in any of products like S-Wedge or Rock Plane, Rock Topple. You can look at dam abutments and the idea of pore pressures and whether pore pressures cause stability issues. So there are numerous numbers of practical applications. Next slide. Okay, so at this point, you probably want to see what RocSlope's all about. So I'm going to hand it over to Julien, and Julien, you can give them a real taste for what the product's all about.
Yeah, I'm excited. Thank you, Brent. So I'll be taking over. Just as a reminder, please, if you have any questions, feel free to type them directly. There should be an area in the GoToMeeting application where you can type out your question, and we will be answering your question at the end of this presentation. So now we'll move into the second part of the presentation. And more specifically, we will look into, how to create a model in RocSlope2 and highlight some of the features which makes RocSlope2 a powerful software for the stability and for your stability analysis. So as mentioned earlier, a kinematics analysis is performed in DIBS, and that allows users to kind of peer into the propensity of failure, whether it be a wedge, planar, or toppling failure. And starting the model creation process in RocSlope2 entails selecting which one among these kinematically feasible failures needs to be taken into consideration. So a wedge analysis examines the stability of sliding blocks formed from 2 or more discontinuities. Planar analysis examines the stability of sliding blocks formed from a single discontinuity. And then you have your toppling analysis, which examines the stability of toppling blocks formed from a single repeated discontinuity at a given spacing. Any one of these analyses can be performed independently from one another or jointly by using the same set of model inputs. In RocSlope2, the true dip of each orientation is used by default to form a block. This is actually what allows for this seamless transition from a kinematics analysis in DIBS to a limit equilibrium in RocSlope2, especially for planar and toppling blocks. And since planar and toppling analyses are typically evaluated as 2D problems, a quick way to convert planar and toppling blocks into equivalent 2D extruded blocks is to set the orientation definition in RocSlope2 to apparent dip. Now, it's important to note that the orientation definition only affects the geometry of planar and toppling blocks. So, as mentioned before, in RocSlope2, the slope geometry only needs to be defined once, and this will essentially propagate to all 3 analyses. Every plane defining the slope is characterized by a dip and dip direction, with the exception of the overall base inclination, which is used for the formation of toppling blocks. In the case of the base inclination, the dip direction is assumed to be the same as that of the slope face. And in addition to the dip and dip direction, users can specify the dimension of each face, such as the slope height, the slope length, whether the slope is overhanging, the bench width, and if the user wanted to define a tension crack, they could do so by specifying the location of tension crack through trace length from the crest, and they could even specify the minimum tension crack area. So typically when users are done with defining their slope properties, they want to move on to define their joint properties. There are 3 joint shear strength models offered in RocSlope2. These are the Moore-Coulomb, the Barton-Bendis, and the power curve. Waviness can also be specified. To model undulations in the joint surface, which will effectively increase the shear strength of your joint. So once we're done setting and defining our joint properties, users are typically interested in defining their joint orientation. Now, this is where RocSlope2 shines, because in RocSlope2, joints are modeled as ubiquitous surfaces, again characterized by a dip and dip direction. And these joint data or orientation data can be imported from dips. Single or separate joint sets can be used when examining joint intersections for wedge failures, similar to how it was done in S-wedge. And RocSlope2 automatically determines which joints contribute to the formation of a planar or toppling block based on the respective kinematic conditions for these failures to occur. Now that we've taken care of the geometrical properties of our slope and block, oftentimes users are interested in modeling the influence of external loads. And once more, most of the model inputs in RocSlope2 are modeled once, and this is actually propagated to all 3 analyses and to each block's form for each analysis. External loads can be applied to the slope face as either pressure loads or point loads, and users can even define a pseudostatic seismic load using a seismic coefficient. Now, with this holistic approach of RocSlope2 to RocSlope stability, support design is even more intuitive and efficient. Users can design support systems which satisfy the safety requirements of all 3 failure modes. The effects of any support types modeled in RocSlope2 is again propagated to every block's form for each analysis type. Spot ball, for example, can be applied to the slope or upper slope surface. And another way to add balls to your model is through our new ball pattern feature, which is very powerful as it automatically places the balls on the face of each block. All you have to do is feed the program the spacing and the orientation of the balls. Shotcrete can also be modeled as a uniform thickness, and it can be added to provide shear resistance along the edges of block. And obviously, this is typically used to prevent spalling of smaller blocks, which cannot be properly intersected by balls. Another important factor in the determination of your rock slope stability is the presence of groundwater. There are 3 groundwater methods in RocSlope2, which models how water forces acts on the discontinuities. We have the elevation option. This essentially allows users to define an elevation, and hydrostatic forces are applied to all submerged portion of block joint surfaces. The other way for users to define groundwater is through a water surface. A user can draw a phreatic surface, and this surface is used to determine the water forces again acting on the submerged portion of the block joint surfaces. Finally, the users have the ability to specify a constant water pressure through the custom pressure option, and this constant water pressure will be acting on the block joint surfaces. Now, on top of water essentially affecting the stability of blocks and water pressure acting on discontinuities, RocSlope2 enables users to model water which are acting on the slope faces through the ponded water pressure. An important aspect of dealing with the stability of wedge and planar blocks is actually the possibility for smaller sized blocks to form. This is as a result of the distribution of joint traces on the slope surface, and RocSlope2 allows users to limit or scale the size of their wedge and planar blocks. And this can be done based on the joint trace lengths, the maximum persistence of the joints, the wedge volume, or the weight of the block. Moving on from steps to create your model, I want to highlight some of the analysis which are accessible in RocSlope2. And like with our other suite of products, it is possible to perform a probabilistic analysis in RocSlope2, where the model inputs are essentially randomly distributed. There are multiple realizations of the model inputs, which are computed for each analysis method, and the probability of failure for each failure mode is reported. In addition to performing a probabilistic analysis, users can also perform a sensitivity analysis in RocSlope2. And this can be done on any blocks formed, irrespective of their failure mode. This usually allows users to understand which model parameters have the greatest influence on the factor of safety. And the sensitivity analysis feature in RocSlope2 enables users to investigate model parameters which the factor of safety is sensitive to. RocSlope2 by default determines the maximum possible block size which can fit into the slope, and this can lead to a conservative probability of failure. So the persistence analysis, which is available in RocSlope2, accounts for the spatial location and the persistence of joints, which can limit the formation of valid blocks. Another analysis which is available in RocSlope2 is the bench analysis. The bench design option in RocSlope2 helps analyze bench scale failures, which can directly influence the overall slope angle. This option, just like the persistence analysis, is an extension of the probabilistic analysis in RocSlope2 for both the wedge and planar analysis, and users can assume either a constant bench width or constant inter-ramp angle from which they can produce the probability of occurrence for various backbreak distances. These information can eventually be used for a quantitative hazard assessment. Now that we've looked at how models are created and what are some of the analyses which can be carried out, let's look at how results are presented in RocSlope2. The default view in RocSlope2 is the all analysis view, which provides a holistic view of the most critical block or the lowest factor of safety block. This helps users make informed decisions faster. The active analysis indicated by the blue frame, as shown here, in the all analysis view enables users to navigate between each analysis to quickly look at other blocks listed in the results grid, which is right underneath our split view here. For a more focused analysis, users can switch to the individual analysis view. The individual analysis view gives users access to a 2D view with the slope and block dimensions annotated. This can be used in the generation of engineering reports. And also accessible in the individual results, in the individual analysis view is the results details, which are available in a collapsible pane for a more for additional results, such as, for example, the normal force acting on the joint or the persistence of the joints forming each block, which is not shown in the results grid. If a groundwater method or ponded water is defined, the water pressure contours can be toggled on in the results tab of RocSlope2. This greatly helps with understanding and mitigating the effects of water pressure, which are acting on the discontinuities or even the slope faces, and allows users to generally visualize the regions of high and low pressure. In addition to the various views that we've spoken about, for any blocks and analysis modes, you are able to generate a statistical plot, especially if you perform the probabilistic analysis. And in doing so, you have access to histograms, cumulative, or scatter plots. Great. So without further ado, I actually want to jump straight into a quick demonstration of RocSlope2. So, but right before that, I would want to actually open the DIPS example file that I'll be using in my demonstration, just to quickly look at the data that we're dealing with. So here's our DIPS example file. We can think of it as the orientation data collected by a geologist investigating a rock face with a dip of 70 degrees and a dip direction of 0 degrees. For this specific file, there are about 283 joints which were recorded. And if you were to analyze these orientation data in DIPS, you could effectively perform a kinematics analysis. And what you're looking at right now is a planar sliding kinematics analysis. And here you can straight away notice that there are a couple of poles here in the critical zone, indicating that out of the 283 planar blocks which could potentially form, 7 could potentially be critical. Let's move on and look at a wedge kinematic analysis. Now, looking at a wedge kinematic analysis, we see that there's an even higher propensity for failure. Here, given our 283 joints that we're analyzing, DIPS is actually considering close to 40,000 intersections, which could potentially form blocks. And out of those 40,000 intersections, close to 13,400 blocks are likely to be critical. So here again, we can see that the kinematics analysis is indicating that there is a propensity for failure, both for the planar sliding and the wedge sliding. Finally, because of the large data set that we're dealing with, we've noticed earlier from the planar analysis that there were a couple of poles on the other side of the slope, and those are typically indicative of anti-DIPS joints, which can form toppling failures. And as we can see from this kinematic analysis, out of the 283 toppling blocks which could form, about 47 is deemed critical. And now that we know that there is a certain propensity for failure, this is where RocSlope2 comes into the picture. So if you were to open a new instance of RocSlope2, this is what you would see. Here we have 3 blocks by default generated based on the default inputs in the program. On the left, you have your wedge block and the factor of safety right above. In the middle, you have your planar block, again, with the factor of safety reported right above it. And finally, on the right, you have your toppling block. And as mentioned before, this is your all analysis view, which kind of gives you a very quick overview of the overall analysis. You can switch between the active analysis by simply clicking in the view containing the block of interest. Here, I've clicked in the middle where the planar block is being displayed, and this has automatically updated the active view. As you can see, this is now highlighted by the blue frame. And in doing so, I now have access to the planar blocks results in my results grid at the bottom. So for the default model, we have 1 block generated for the wedge analysis, 1 block generated for the planar analysis, and 1 block generated for the toppling analysis. So let's go right ahead and start modeling our slope. And like with all of our programs, we want to start with defining our project settings. So users of our programs will be familiar with a lot of the parameters which are required here. The units, is a model input that is required. And for the sake of simplicity and for this example, we'll just leave it as a defaulted value, which is using a metric stress system. Moving on to the analysis, which goes over which of the three analyses is taken into consideration. We can see that by default, all three analyses are taken into consideration. We'll leave it as that for this example. And as mentioned before, we have the orientation definition. Again, for this example, we'll just keep the default use through div. If you have wedge analysis selected in the analysis methods, you will have access to the wedge settings. Here, the wedge settings is analogous to your project settings in SWedge, which enables you to tell the program whether to consider the intersection of only two joints or a third joint through a basal joint set. We'll keep it simple and we'll stick to the wedge shape for this example. And if you have a toppling analysis being considered in RocSlope2, you will also have access to your toppling settings. And this is, again, analogous to your project settings in RocTopple, which gives you the ability to control how your blocks are being generated through one of these two methods. The equal area is one of them, and Goodman and Bray being the other one. And you can also choose which specific toppling model you want to investigate. Here, the block toppling model essentially accounts for you could call it three modes of failure: the toppling mode, the sliding mode, and whether a block is stable. If you were to select the block flexural toppling model, two additional modes of failure would be accounted for, being shearing and flexural bending. Statistics goes over any sort of parameters which might be required were you to perform a probabilistic analysis. And since we're performing only a deterministic analysis, we'll leave it as is. And finally, you have access to design standards if you were to perform a design analysis. But for this example, we'll leave it as is. Clicking OK. And now that we have our project settings defined, what we're interested in is defining our slope geometry. We can do so by simply clicking on the geometry icon here in the toolbar. This will bring forward this slope geometry dialog, and we'll essentially enter the same values that was used for the kinematic analysis that I showed previously. So we had a rock face dipping at an angle of 70 degrees. And if I remember correctly, the dip direction was set to 0 degrees. Let us consider a slope having a height of 20 meters, a length of 40 meters. And as far as the upper face is concerned, we'll leave it flat. So we'll leave the dip value to 0, and we'll just make sure that the dip direction is the same as the dip direction of the slope face. Finally, I want to consider a bench width of 10. And once we've entered these values, we can simply click OK. And the beauty of RocSlope2 is that computations are triggered automatically. As soon as the user enters model inputs to the program and they click OK, the computation are triggered automatically and shows you the effects of changing these parameters on your analysis. Here, for the default orientation data set that is provided and with the geometry parameters that I've entered, we can see that 2 blocks are formed for the wedge analysis. Again, this is showing by default the minimum factor of safety block, but we could choose to look at another one, and this is the other one which is formed for the planar analysis. With the default orientation data set provided, there's only one planar block which is generated, and for the toppling analysis, there are no toppling blocks generated. Once we're done setting our slope geometry parameters, we're often interested in making sure that we have our slope properties set correctly. Here you can set the unit weight of the slope. For the sake of this example, again, I'll just keep it as a defaulted value of 26. And if there was ever the presence of a groundwater or ponded water, you could enter these values or model your groundwater here in the slope properties. But, for this example, we'll use a defaulted value. So now that we have the slope taken care of, we move on to defining our joints. We'll start with defining our joint properties. So by default, you have 2 joint properties, which are defined when you open RocSlope2. And as mentioned before, you have access to various shear strength model. So for joint property 1, let us leave the defaulted values as is. I'm not too interested. Most of the joints which will be used for this example will use joint property 1 and will use these values defaulted at a cohesion of 0 and a friction angle of 35. For joint property 2, because we'll be performing a toppling analysis as well, and when performing a toppling analysis, there is the presence of a release joint, which is the base joint. Let us enter a value for this release or base joint, which is contributing to toppling blocks. I'm going to call this base joint and set the value of the friction angle to 38 and click OK. Now that I have my joint properties set, I want to go into the orientation dialog, and unlike S-wedge, rock plane, and rock couple, there are a couple of new parameters which are required from the user so that we can transition from a kinematic analysis seamlessly into this limit equilibrium analysis that we're performing. These new parameters are essentially your planar sliding limits, which is the same as the planar sliding limits used in a kinematics analysis. This determines which joints in the list should be taken into consideration when forming a planar block. If you have a toppling analysis enabled, these are the toppling analysis settings that you need to provide the program so that it knows among all the joints which is either imported from DIBS or is being accounted for this specific analysis, which among them will form a toppling block. These settings essentially comprise of a toppling lateral limit, which is analogous again to the planar lateral limit, and you have to provide the joint spacing. We'll leave these as is, with the exception of setting the base joint property to that base joint that we've defined earlier. Now that we have these parameters set, let me go and import my DIBS data. You can do so by simply clicking on the import DIBS, and here straight away you can see that there are 283 joints which were imported, same number that you saw in the data grid in DIBS, and clicking OK will again just trigger the computation, and in a matter of just a few seconds the limit equilibrium analysis will be performed for all 3 analysis modes. And there you go. Here again, by default, the program will show you the minimum factor of safety block for each analysis mode. And from the get-go, I can see that for each analysis mode, I have blocks with a factor of safety less than 1, which are forming. Therefore, these are of interest to me when I'm designing my slope. The other thing of interest is the fact that I have my wedge and planar blocks, which have the lowest factor of safety. So when designing perhaps a support system, my focus will be trying to reinforce the slope against these 2 modes of failure. Here we have the active view, the active analysis view as the wedge analysis. And so if you look at the results grid, let me scroll down to the bottom, you'll notice that there are about 30,200 blocks generated. This is very close to the number of critical blocks that was reported in DIBS. And just by clicking on any rows here, you are able to basically bring the block of interest in focus. You can also sort these columns in ascending order or descending order of any of the parameters, which can be very useful. Moving on to the planar analysis, we can see that there are about 6 blocks which have formed given the data provided. And again, this is very close to the number of blocks reported in the kinematics analysis. Thus, again, we can actually go and look into more details if we wanted to by simply double-clicking in the view of interest. Here, I'm looking at this specific planar block, and double-clicking here will just bring me into this individual analysis view. And in the individual analysis view, I can have access to more detailed results, such as, for example, the planar plane length, or even the normal force or the normal stress acting on the joints. We can navigate among each views through the tabs here or in the analysis window in the toolbar. And double-clicking again in the view will just bring you back to this all analysis view. Another feature which I think is going to be extremely useful to the users, since we're dealing with thousands of results, is the filter option. Here, and you know, a quick example of how this could be used, because engineers are typically concerned with blocks whose factor of safety is less than 1, we can set the upper bound for the factor of safety to 1. And as I'm sure you've noticed, there were a lot of blocks which were very thin slivers, and those very thin slivers are usually not interesting for analysis purposes, because those have volumes, very small volumes, close to 0. So again, we can use the filter to filter those out. I can choose to set a lower bound for my volume to 400. This will drastically reduce the number of results in my results grid as shown here. Moving on to the results tab, where even more information is accessible. Users can actually look into factor of safety distribution for each analysis mode. They can do so by simply clicking on the histogram here. They can even highlight the data for those blocks whose factor of safety is less than 1, and they can even chart the best fit distribution for this data. Here I'm doing that for the wedge analysis, and here I have my distribution. I can switch between the analysis mode very easily by just clicking change plot data. Now I'm looking at the distribution of factor of safety for the planar analysis, and I can even do so for the doubling analysis. Finally, one last result visualization tool / feature, which I think is very neat and could be extremely useful to users, is looking at scatter plots. Again, we're dealing with a large amount of data here, and at times the user might be interested in looking at the relationship between the factor of safety and any sort of input parameters or even an output parameters. Here, for example, let us look at the relationship between the factor of safety and the wedge volume for a wedge analysis. Again, we gave the users a lot of options. They can highlight the data for those blocks whose factor of safety is less than 1, and they can even plot a regression line to look at the trend of this data. Here, I click OK, and there I go. There you go. You have your scatter plot, you have your regression line, and you have all your blocks whose factor of safety is less than 1 highlighted. A lot of inferences can be made from these charts. As you can see, as the factor of safety increases, the volume of the blocks are very small. So we could effectively use this data again to go back to the individual analysis view or even the all analysis view to further filter the data that we're interested in. So this was really just a quick overview of how you can use RocSlope2 and what are some of the cool features in RocSlope2. So I want to leave about 10 to 15 minutes for the Q&A session. So this brings me to the end of my demonstration, and I think that's it.
Thank you very much.
Thank you.